All right, today we're going to do section 2 of chapter 8. That deals with trigonometric integrals. 4:14. Today is day 18. It's the end of the 9th week. Chapter 8, section 3, trig integrals. All right, so looking at these, what we're going to be looking at are how do we derive and how do we solve integration with respect to trigonometric identities. So the first part, if we took the derivative of two functions, u of x and v of x, we'd use the product rule. So we have u of x, v of x, and the derivative is u prime of x, v prime of x. So the derivative of u of x, v of x is equal to u prime of x times v x plus u of x times v prime of x. Now, that's derivative. We're used to that. Now we have to go backwards. Because we know where this came from. If we integrated this whole thing, u prime of x vx dx plus the integral of ux v prime of x dx. So what's that going to get us? Now we know what the structure we have. And if we rearrange these things, because what we want to do, we want to get into a simpler part where we have this page. There. What we want to have this form on the other side. Because what we want to do is we want to get it to a form of ux v prime of x dx. Because this is the form that we want to make our equations as we start going further. So solving for this one, I move this over there, so I have that ux dx, not dx, minus this integral, which is u prime x vx dx. And now, this is the form that we'll be using for this entire section. Actually, the rest of the course. The way it's set up was we have a product of two functions. You want u to be the part that's easily differentiable. In other words, you can take derivatives of it pretty easily. And you want the u prime piece to be the part that's easily integrable. So you can easily take the derivative of the u of x multiple times without until you get to zero, and then you take the integral of v prime. So this is the structure that we're trying to get to, because what we want to be able to is take any product of a function that's made up of a product of two or more terms and be able to integrate those readily. All right. So let's look at our first example. I apologize. The printer machine was broken, so I couldn't give you all your sheets, which it makes it much easier, but I couldn't do it today. So let's look at example one. It says find the integral of x cosine x dx. So the question here is, of those two, which one do we make u? Which one do we make v? Let me switch over here. Remember, let's go back to our formula. What we wanted to do is have ux v prime of x dx. Oh, I forgot to say, the integral of this one, since it's the integral of a derivative, the formula now becomes, because the integral of a derivative is simply the function minus the integral of u prime x v dx. So this is the up-to-date version. I forgot to do that. So we want u prime of x vx dx. So in order to do this, in order to take the integral of this, because right now we don't have a rule of integration for a product like this. It's not cosine u du. So what is our first objective? What we have to do, we have our function here. We have to define what is our u, what is our v, because then we got to take the u prime and the v prime. Remember, the u has to be differentiable and the v has to be easily integrable repeated times. So in this case, we'll set x to be the u factor and cosine x to be the v factor. Because if we did it the other way, if we did cosine x to be the u, we can take derivatives forever. We'd never stop. And then if x was our integral, we could integrate it. Then we get x squared over 2, x cubed over, I mean, we keep on going forever and ever. X cubed over 6, x to the 4th over 24, and it would never stop. So there'd never be an end. We have to set it up so they're easily done, but there's also a finite number of them. The derivative of x is 1. The derivative of cosine is negative sine x. But here is saying that the v prime is cosine. If that's cosine, then the v would be what? If our function remember, this is this. So our u is the x, our v prime is the cosine. So to find u prime, we take derivative. To find the v, we integrate this. Integral of cosine is sine. So now we have the pieces we need. So the integral of x cosine x dx is equal to u, which is x, v, which is sine x, minus the integral of u prime, which is 1, times v, which is sine x dx. So our answer is going to be x sine x minus, what's the integral of sine? Remember the unit circle? Here's sine, cosine, negative cosine. Derivatives go this way. Integrals go that way. So the integral of sine is negative cosine. plus C. All right, let's look at the original equation. Remember, the first thing we had to do, we had to define our u and our v prime. Because our formula because we have to find u and v prime. We have two choices to choose from. So let's see the different possibilities. We could have done, this is for u and this is v prime. We could have gone x cosine x, cosine x or x, and we can start it that way. Because for this one, we got to differentiate it. And this one, we have to integrate it to find the other one. And conversely, we could have found 1 and sine, or sine and, or this one would be negative cosine. Remember what we said last chapter? Whenever you have these formulas, just try it. If it works, it works. If it doesn't, move on to something else. So the choices of u and v prime are important. So that we have a function that is solvable. Because if you pick the wrong order of the u, v prime, then what you could be faced with is setting up equations that aren't solvable. All right, let's look at example 2. ln x dx. Remember, well, why is this one important to us? Do we have any formula for the integral of ln x? No. We know that the derivative of ln x is 1 over x. But we don't have an integral for ln x. So this is where we have to do integration by parts, which is what we're doing for this section, integration by parts. Do we have two functions here? Do we have a u and a v? Remember, the u's we differentiate, and the v's we integrate. So, are there two functions here? There's a 1 in front. So it is two functions. Now we have to decide which one is u, which one's v prime. Again, we only know the derivative of ln x. So since we only know the derivative of ln x has to be the u value. And v prime has to be the 1. So what's the derivative of ln x? 1 over x. What's the integral of x of 1? X. So now we have the 4 pieces. Now we can start plugging them in there. We have u and v. So we have x ln x minus the derivative of this 1 over x times v, which is x. We have x ln x. The x's cancel. So we have the integral of 1 dx. So there's your answer. There's your integral of ln x dx. Again, the choice of u and v prime is important, because if we would put v prime as ln x, what's the integral of ln x? We don't know that. Now we do. Let's look at example number 3. X squared e to the x dx. So there's our formula. We have to try to get this equation into that. So we have to figure out what our u and v prime numbers are. Well, since x squared, if we take the derivative, it's finite because first one will be 2x, then the next one will be 2, and then next will be 0. So it's a finite one. So we're going to use u as x squared. And the v prime will be e to the power x. We just defined what both of those were. So the derivative of x squared is 2x. The integral of e to the power x is e to the power x. So it equals u times v, which is x squared times e to the power x minus the integral of 2x e to the power x dx. That gives us x squared e to the power x. The 2 is a constant. It comes out. But we're back to the problem. We're back to the same problem. We don't know the integral of x e to the x. So we got to do it again. So we got to figure out what our u is and what our v prime is. Again, x is the easiest one to take derivative because it'll be finite. E to the x, we can integrate it infinitely. So the derivative of x is 1. The integral of e to the x is e to the x. So here we have our 4 pieces. So now we have to do this again. So inside here, we're going to have another u v u prime v dx. That's what we have to do with this. X squared e to the x minus 2. U is x. V is e to the power x minus the integral of 1 e to the x dx. X e to the x. The integral of e to the x is e to the x plus c. Because it's in an indefinite integral, just remember, I can't forget the plus c. X squared e to the x minus 2x e to the x minus 2 e to the x plus c. So there's that answer. You may have to repeat the process over and over and over until you get to a finite. See, this is how come we want the derivative part to eventually go to zero. Because if it didn't go to zero, if we reversed them, then we'd keep on doing this forever and ever and ever, and never get a solution. Because the integrals will just get larger and larger and larger and larger. Okay, let's look at example 4. E to the x cosine x dx. Again, uv prime dx equals uv minus u prime v dx. This is the formula we need to use. Okay, the problem with this one is that it's never ending. Let me see if I wrote this one down correctly. Yeah, because it's going to be never ending. Oh well, we'll look at this one. All right. So we'll do e to the x and cosine x. That means u prime is e to the x and v is sine x. So u is e to the x sine x minus e to the x cosine x. With the dx, not 2. Okay, so what can we do now? Yes. Oh, this is example 4. Sorry. See if I wrote again. Yeah, that's what we got. So what would we do next? Because if you look at it, we're back to the beginning on this one. If we did it again, we have e sine x, ex sine x minus parentheses e sine x minus. Did it again, then it cancel out. If I add both sides, ex cosine x dx. So back to our original equation, we divide both sides by 2. Let me look at this. I think I took a wrong turn somewhere. Okay, yeah, that's what I just did. Well, this the e to the cosine. So after I have my e to the x, e to the x, and that's So now we're stuck in an endless loop. Okay, yes. At this stage here, since both of those are the same and we haven't gotten any further, we reverse. Since we did it this way the first time and didn't eliminate it, so if we reverse them, then that would be the part that eliminates it. So derivative of cosine is sine. Integral of EX is EX. So we're going from here to here now. We have e to the x cosine x dx, because every time if we keep on doing this the same order, we're always going to have a repeat of this one. So we'll do the other way. We repeat the process. So we have the uv, which is e to the x cosine x minus the integral of sine x e to the x dx. No, derivative of cosine is negative sine. Negative sine. Impose again. We have example 4. Integrate EX cosine x dx. We have to define those variables. So we're going to say with this one cosine and this one e to the x. All right, so uv prime dx is equal to uv minus u prime v e to the x cosine x equals e to the x sine x minus the integral of e to the x sine x. Okay. Oh, yeah, duh. Okay, now we have to redo this one. U is e to the x. And v is sine x dx. So with this one, we have to do it, repeat the process. Ex sine x minus u prime is e to the x. This is v prime, so it's v is negative cosine. So it's uv is e to the x negative cosine x minus the integral of u prime ex v negative cosine x dx. Yeah, I had to use these now as UV. This is my original UV. Now I have to redo it with these. I did those twice. I shouldn't have. E to the x sine x. Negative and negative makes it a positive. This goes out in front. Oh no. Yeah, so that makes it a positive. This makes it a negative. Negative, negative, positive, and distribute. Yeah, okay. That's where it is now. Since it's going to be repeating, only things that happen each time. If I keep on going further, I'll get another ex sine x. Then I do that again. I get ex cosine x. So I move that over there. I get 2 ex cosine x dx. Ex sine x plus ex cosine x plus c. It's going to be a plus c eventually anyway, because it's integral. And divide by 2. So my original function is equal to e to the x sine x e to the x cosine x over 2 plus c. It'll keep on repeating itself. Uh-oh. I don't have my charger. Okay, obtain a formula that expresses the integral. This is example 5. Integral of cosine n x dx in terms of an integral of a lower power of cosine. Obtain a formula that expresses the integral of this in terms of an integral of a lower power of cosine. All right, so we look at this as